This video covers concepts 3.3 and 3.4, carbohydrates and lipids. Carbohydrates include sugars and the polymers of sugars. The simplest carbohydrates are monosaccharides, or simple sugars. Carbohydrate macromolecules are polysaccharides, polymers composed of many sugar building blocks. Monosaccharides have the molecular formulas that are usually multiples of CH2O. Glucose, shown here as one of the 6 carbon sugars, is the most common monosaccharide. It's C6H12O6. Monosaccharides are classified by the number of carbons in the carbon skeleton and the placement of the carbonyl group. Though often drawn as linear skeletons, in aqueous solutions many sugars form rings, including glucose. You can see how that process works. You got linear rotation of the carbon bonds, and you get an ester bond formation to complete the ring and the ring structure. And this is the ring structure for glucose. A disaccharide is formed when the dehydration reaction joins 2 monosaccharides, and the covalent bond formed is a glycosidic linkage. So here's the dehydration process to form a glycosidic ether bond linkage. This example is a disaccharide sucrose, which is formed by the covalent bonding of glucose and fructose to make the disaccharide sucrose. Polysaccharides, these are the polymers of sugars, and they have storage and structural roles. The structure and function of a polysaccharide are determined by its sugar monomers and the positions of glycosidic linkages. Starch is a storage polysaccharide of plants consisting entirely of glucose monomers. And plants store surplus starch as granules. The simplest form of starch is amylose. Glycogen is a storage polysaccharide in animals. And humans and other vertebrates store glycogen mainly in the liver. The polysaccharide cellulose is a major component of the tough wall of plants. Like starch and glycogen, cellulose is a polymer of glucose, but the glycosidic linkages in cellulose differ. So you have the 1,4 linkage in starch, and you have 1,4 alpha. You have 1,4 beta linkages for cellulose. In starch, the glucose monomers are arranged in alpha helical formation. That's due to the alpha 1,4 glycoside linkages. In cellulose, monomers are arranged in the beta 1 linkages, and you get linear molecules, and they come out in parallel and they are cross-linked to form fibers by hydrogen bonding. These microfibrils provide mechanical strength in the cellulose plant cell wall. Enzymes that digest starch by hydrolyzing alpha-1,4 linkages can't hydrolyze beta linkages in cellulose. So cellulose is known as insoluble fiber in human, and it passes through the digestive tract. Some microbes use enzymes to digest cellulose. And many herbivores, cows and termites, have symbiotic relationships with these microbes. Chitin is another type of structural polysaccharide found in exoskeleton of arthropods. Chitin also provides structural support for the cell walls of many fungi. Now, chitin has an amide group, so that makes it different than these glucose-based starches and cellulose. Moving on to lipids, which is section 3.4. So fats are constructed from two types of similar molecules. Two types of smaller molecules, glycerol and fatty acids. So here's the glycerol in the gray, and here's the fatty acid. Glycerol is a 3-carbon triol alcohol, and the fatty acid is a long hydrocarbon skeleton with a carboxylic acid group on the end. So fatty acids interact and form ester linkages with the glycerol, and that forms a fat. In this case, you have a triacyl, or 3 fatty acids joined to the glycerol to form the triacylglycerol fat molecule. Fats made from saturated fatty acids are called saturated fats and are solid at room temperature. Saturated means there's no double bonds in the hydrocarbon portion of the fatty acid. Most animal fats are saturated, like butter. Fats made from unsaturated fatty acids, they're plant-derived and from fish fats as well, in this case olive oil. And here you'll have some unsaturated lipids, meaning they have one or more double bond. One important molecule in the cells is a phospholipid. It has 2 fatty acids connected to a glycerol, and then a phosphate group with sometimes some other chemistry attached to that, attached to the 3rd hydroxyl group on the glycerol. So the 2 fatty acids are hydrophobic, and the rest of this, the glycerol, the phosphate, and any functional group like the choline is hydrophilic. And when you add these to water, they self-assemble into bilayers. And this is what you find as the basis for cell membranes. Steroids are characterized by a carbon skeleton consisting of 4 fused rings. Cholesterol is an important steroid shown here, and it's a component in animal cell membranes. Cholesterol is a molecule from which other steroids, including sex hormones, are synthesized. Although cholesterol is essential in animals, high levels in the blood may contribute to cardiovascular disease. That's the end of this particular video.